Welcome to week 19 of Algebra 1 with Mrs. Whybark. This week we will be learning about factoring. We are going to look at two specific methods for factoring. The first is factoring by distribution, followed by factoring trinomials. Our first topic is factoring by distribution. You should record these notes on the handouts for week 19 video notes. These are available on the class Moodle website and will also be handed out in class.
In this lesson, we are going to factor by putting our algebraic skills in reverse.
What do you mean, in reverse?
Recall how to use the distributive property to multiply a monomial by a binomial. This expression represents the product of a monomial and a binomial in one variable. So you see that multiplication of a polynomial by a monomial is just an application of the distributive property. Now it's time to learn how to factor. Factoring is the reverse of multiplying. In this lesson, we will factor polynomials. Factoring a polynomial means rewriting the polynomial as a product of simpler expressions. Now let's look at this problem in reverse.
I think I see what you mean about working in reverse. But how does it actually work?
The distributive property allows us to factor.
Recall that when a quantity A is multiplied by a sum, A is distributed to each of the terms inside the parentheses. Notice how on the right side of the equation, A is a factor of both monomials, AB and AC. A is a common factor of AB and AC.
That makes sense. It's a factor common to both expressions. The distributive property can also be written like this.
AB plus AC is equal to the product of A and the quantity B plus C.
In a polynomial where there is a factor common to each term, that factor can be factored out or removed, and is one of the factors when the polynomial is rewritten as a product.
When we factor a polynomial, the first thing we should do is factor out the greatest common monomial factor.
Greatest common monomial factor? What's that?
The greatest common monomial factor of a polynomial is the common factor that has the largest numerical factor other than 1 and the highest degree in each variable.
While this refers to the greatest common monomial factor, in class we usually just call it the greatest common factor, or GCF for short, and that's how you will see it referred to in your textbook.
Let's factor the polynomial expression x squared plus 3x.
We are going to factor out the greatest common factor. To find the greatest common factor, factor each term.
X squared is x times x. And 3x is the product of 3 and x. The only factor common to both terms is x. So, x is the greatest common factor.
Now we use the distributive property to rewrite the expression. Write the greatest common factor, x, on the outside of the parentheses, and the remaining factors, x and 3, inside the parentheses.
We get x times the quantity x plus 3.
Great job.
Let's try another one. Factor the expression 4x squared plus 4x plus 8.
This is example 2 on your notes. Please write down all the factors and then the final solution. Also write down what the greatest common factor is.
First, we need to find the greatest common factor. 4x squared is 2 times 2 times x times x. 4x is 2 times 2 times x. 8 is 2 times 2 times 2. The greatest common factor is 2 times 2, or 4.
Use the distributive property to get 4 times the quantity x times x plus 2. Or 4 times the quantity x squared plus x plus 2.
Good work.
Sometimes in class, we like to refer to this method as using the GCF and leftovers, because what we're really doing here is taking out the greatest common factor, which in this case is 4. If I divide each of these terms by 4, what's left over is what goes in the parentheses. So in other words, 4x squared divided by 4 is x squared. 4x divided by 4 is x, and 8 divided by 4 is 2. So Miss Wiltsey in particular likes to call this the greatest common factor and leftovers. So you'll hear us say that frequently.
If possible, factor x squared plus 4y.
We start by factoring each term. X squared is x times x, and 4y is 4 times y. These terms have no factors in common.
That's right. There is no common monomial factor in these expressions.
Do you remember what we call something that doesn't have any factors besides 1 and itself? We call it prime.
In question 1 of your guided notes, factor 6x plus 12.
Begin by factoring each term. 6x is 2 times 3 times x. And 12 is 2 times 2 times 3. The greatest common factor is 2 times 3, or 6. Use the distributive property. The answer is 6 times the quantity x plus 2.
You're doing great with these polynomials. Now, let's look at some that are a little more complicated.
Let's factor the trinomial 8r squared s minus 2s squared plus 6sy cubed.
The coefficients 8, 2, and 6 have a greatest common factor of 2.
R is not common to each term. It won't be part of the greatest common factor. The highest degree of s, common to each term, is 1. So that gives us s.
Y is not common to each term, so it won't be part of the greatest common factor. The greatest common factor is 2s.
Now, we divide all 3 terms by 2s to get the other factor. It's 4r squared minus s plus 3y cubed.
This is what the first page of your completed notes should look like. If needed, please take a moment to pause and catch up. I would specifically like you to indicate what the greatest common factor is in each of the 5 examples. Next, we will be discussing factoring trinomials of the form x squared plus bx plus c. This means that all of these trinomial examples have just one x squared.
Today we will study how to factor a trinomial of the form x squared plus bx plus c, where b and c are real numbers. All of the trinomials we will factor in this lesson have a quadratic term with a coefficient of 1. Remember, factoring is the reverse process of multiplying. So let's start by talking about how we multiplied two binomials. Who remembers how we multiplied two binomials?
I think the easiest way is the FOIL method. FOIL stands for first, outer, inner, last.
You're right, Lizzie. As an example, let's multiply the quantity x plus 4 by the quantity x plus 6.
First terms. X times x is x squared.
Outer terms. X times 6 is 6x.
Inner terms. 4 times x is 4x.
Last terms. 4 times 6 is 24.
Combine like terms. 6x and 4x is 10x. The product is x squared plus 10x plus 24.
So, the first term in the trinomial is the product of the first terms in the binomial factors. The last term in the trinomial is the product of the last terms in the binomial factors. And the middle term in the trinomial is the sum of the outer and inner products. Factoring is the reverse of multiplying. So to factor a trinomial, think of FOIL in reverse. If we factor x squared plus 10x plus 24, we get the quantity x plus 4 times the quantity x plus 6.
So let's learn how to reverse the FOIL process.
To see how this is done, let's factor the trinomial x squared plus 10x plus 24.
We're looking for two binomials. From FOIL, we know that the product of the first terms of the binomials must be equal to x squared.
X squared is x times x. So x is the first term in each binomial.
The last term of the trinomial is 24. So the product of the last terms in the binomial factors must be 24.
But we don't know which factors of 24 to use because the choice of factors affects the sum of the outer and inner terms.
The middle term of the trinomial is 10x. The sum of the outer and inner products must be 10x. So the constant terms in the binomial factors must be two numbers whose product is 24 and whose sum is 10.
For each of the 6 examples that we are going to look at, I would like you to include this small table that lists the factors, in this case of 24, and the sum. This is a good habit to get into as you're learning to solve trinomials of this form.
Start by listing pairs of factors whose product is 24. Stop when you find a pair whose sum is 10.
1 and 24 have a sum of 25.
2 and 12 have a sum of 14.
3 and 8 have a sum of 11.
4 and 6 have a sum of 10. Bingo!
So positive 4 and positive 6 are used to complete the binomial factors. X squared plus 10x plus 24 factors into the quantity x plus 4 times the quantity x plus 6. Let's multiply the factors to make sure our answer checks. Using FOIL to multiply the factors, we get x squared plus 6x plus 4x plus 24. Combining like terms gives us x squared plus 10x plus 24. Because we got the original trinomial after we multiplied, it checks. For the rest of this lesson, we will not always show the checks, but you should always check your factoring by multiplying. Let's summarize what we have done so far. When we factor a trinomial of the form x squared plus bx plus c, we get two binomial factors of the form x plus r and x plus s, where r and s are constants.
The product of these constant terms is the last term of the trinomial. Therefore, r times s is equal to c. The sum of the constant terms r and s is the coefficient of the middle term in the trinomial. So r plus s is equal to b.
In question 1 of your guided notes, factor the expression y squared plus 10y plus 9.
Should I look for a common factor first?
Yes, you should always begin each factoring problem by looking for a common factor to factor out. Because we are learning a new factoring technique, none of the problems in this lesson will have a common factor to factor out.
Okay, the binomials will each have a first term of y because y times y is equal to y squared.
The second terms must have a product of 9 and a sum of 10.
1 and 9 have a sum of 10. Woohoo! The trinomial factors into the quantity y plus 1 times the quantity y plus 9.
Remember to check your answer. Things up a bit and factor trinomials that include negative signs.
Bring it on!
We can do it.
Okay. Factor the expression h squared minus 5h plus 6.
Well, the first term in each binomial is h, because h times h is h squared. The second terms must have a product of 6 and a sum of negative 5.
Be careful here. The factors have a negative sum and a positive product, so each of them must be negative.
Why?
At least one of the factors must be negative to produce a negative sum. If the other factor is positive, then their product will be negative, not positive. So both factors must be negative.
Okay, I follow that. So the factors could be negative 1 and negative 6, but their sum is negative 7.
Negative 2 and negative 3 add up to negative 5. So the factors are h minus 2 and h minus 3.
I checked it using FOIL, and it works.
Factor the expression j squared minus 2j minus 8.
J times j is j squared.
This time, we're looking for constant terms whose product is negative 8 and whose sum is negative 2.
What do we know about the signs of two numbers when their product is negative?
We know they're different. One positive and one negative.
Right. So pick pairs of factors with different signs.
1 and negative 8 add up to negative 7, so that's not it. Negative 1 and 8 add up to positive 7, so that's not it either.
2 and negative 4 add up to negative 2. That's it! The factors are j plus 2 and j minus 4. It checks.
Factor, if possible, the expression x squared plus x minus 1.
The first term in each binomial is x.
We're looking for numbers with a product of -1 and a sum of +1.
The product is negative, so the signs must be different. They're 1 and -1.
Not so fast, Ferd. 1 plus -1 is 0. Mr. Frogan, these are the only factors of -1, and they don't add up to 1. Does this mean that we can't factor this trinomial?
Yes, Lizzie, this trinomial cannot be factored. Not all trinomials can be factored. We say this type of trinomial is prime, which means it is not factorable. In question 3 of your guided notes, factor the expression k squared plus 8k minus 20.
The first term in each binomial is k.
Now we need two terms with a product of -20 and a sum of 8. Since the product must be negative, we know we should try factors whose signs are different.
They could be -1 and 20, but their sum is 19.
1 plus -20 is equal to -19.
2 plus -10 is equal to -8. We're getting closer.
It's -2 and +10. Their sum is +8. This trinomial factors into the quantity k minus 2 times the quantity k plus 10. I did the check mentally.
This is what the second page of your completed notes should look like. Please be sure that you included examples of the factors and sum tables for each example. It's very important to understand this method for helping you to factor trinomials of this form. If you need to take a moment and catch up, please do. Thank you for watching this Whybark production.